Yo, yo, yo. What's up, what's up? Welcome back. Today we're working on my x86 operating system, written in Rust for fun, right? We're just here to learn how operating systems work, try to get like a good feel for what's going on under the hood, etc., etc. So right now we have like this operating system that boots. It has like memory allocation, not paging, just allocation. It can like log to the serial port and to like VGA output. It has unit testing and support, and can read and write the clock. Actually, this should say clock here. It can talk to the PCI bus, and it can run like async await code in Rust. It's pretty cool. Today we're working on the network card. So we're working on this like, how do I find it here? One sec. The RTL 8139, which is a PCI card that has an Ethernet port in the back, and this handles transmission and receiving of Ethernet frames. And we're working on getting like a nice little driver hooked up to this guy to do all the right things. So far we've done a couple rounds of this. We've been working on this for 2 streams now. And the first stream we were kind of figuring out like how we like transmit, what does that look like, and now last stream we kind of got a feel for how does receiving look like, and now we want to figure out, well, how do we actually like write that into a driver that's usable. So last stream there was a couple things that were a little unknown when we left it off, and it's because I hadn't found this programming guide. So the sending we had like pretty down pat, but the receiving side was a little more confusing, and it turns out there's like this programming guide that has more information than the datasheet on how you're supposed to handle all this stuff. So there's probably going to be a little bit of extra testing here to figure out that I understand this correctly, but I've given this a read, well, skim offline, and as far as I understand how this driver should work, we have code running on our CPU, and we have the PCI subsystem that we talk to through I/O ports. So this guy comes through here. This guy has the network card plugged in, so net. Right? So we talk to the PCI bus. Step 1 is, let's pick a better color for this. This is step 1, and 1 is ask PCI bus about card. So he's going to tell us information like what interrupts does the card give us, what memory ranges does he, like how do we, like where is he mapped, like how do we talk to the card directly. So the card also has connections to IO as well as memory. Oh gosh, that's too small. Memory. So this guy talks to him, and this guy talks to him. And so we like ask the PCI device, like, hey, where are these lines going? And he also has connections to interrupts. Like this. Details missing here. Then we now can have these like memory lines directly to the card, and so we're going to use those. And so this is step 2 is like this connection. Call this 2. And step 2 is set up card through registers, through memory mapped registers. And then step 3 is also using this connection, and he is like transmit and receive data. Like that. Okay. So nothing too crazy. The way that this works is, I think it's already open. There's some like initial setup that we have to do. Like we reset the device with like a software interrupt. We create a buffer and we upload that, or we like give the address of that buffer to the card. So the card can access memory directly. And so we give it like a physical range of memory and say like, when you get data, pump it in here. We tell it that we want interrupts for certain types of behavior. And then we tell it we're ready to start, like you can receive data now and we might transmit data to you. Then there's this like transmission code, and what the how transmission works is you give it a pointer to some data, and then when you're done with that, or then once you've given it to it, you can tell him to start transmitting. You give him like this configuration that's like, hey, here's how long the data is, and like let me know when you're done, stuff like that, and you say like, okay, go, and it sends the data. And on receiving, there's this like circular buffer that like we uploaded that like range of memory to the machine or to the card. And what happens is we have like packets that come in, and we maintain like this, I think it's capper. There's 2 registers here. It's basically a circular buffer. And the circular buffer tells us like where we have 2 pointers, right? To the start of the buffer and to the end of the buffer. The card will increment the end of the buffer. So as it adds new data, it will increment the end. And we have to increment the start as we read data, right? So after we've read something, we can go, okay, we've read that. Now you can write up to this point, if I understand this correctly. See, capper is the read pointer, which keeps the address of data the driver has read. So I think when we read, we basically get a packet, we look at it, and then we increment that capper pointer, if I understand correctly. Let's double check. Capper. Process of packet received. Data is received from the line. When early received threshold is met, it goes to the receive buffer. After the whole packet is moved to future receive buffer, the receive packet header is written in the front of the packet. CBA is updated to the end of the packet. So CBA is that end pointer, I believe. These are set to OK, and ISR routine is called, and the driver clears this and updates the read pointer. So I think we can do those 2 separately. I think that what I want my driver architecture to be is I want the interrupt to do very little here. I want the data to be read probably outside the interrupt. And then maybe we do like card negotiation over there as well, etc. Yeah, so let's take a look at that. So what we've had so far is we have a demo, or when I run cargo run, sorry, there's a sleep that happens before we quit, and I'm just gonna disable that really quick. 1 sec. That's here. Let's just turn that off temporarily. Okay. So we have a demo here where we send some data over the network card, these FFFs, and then we wait. We ask the card to like pipe back anything it sends back into itself, and so then we receive that same data we write, and that's like FF. And the format of this data is 16 bits of header, 16 bits of length, and then data. And so right now we just kind of assume that our data is at the beginning of the buffer, but really we need to like check where we've started, where to read from. So the first thing we probably have to do is start making use of this capper register that we saw on the datasheet or the programming guide. And then on transmission, there's actually 4 transmission buffers, and we have to cycle through them appropriately, which means that we have to keep track of which one we've sent to before. And I think that we just have to remember that in the driver. Let's double check that here. Packet transmission. So there's 3 of these addresses and 3 statuses. And copy the packet to continuous buffer memory, write the scripture which is functioning, blah, blah, blah. As the number of data meets the blah, 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 whole packet interrupt service is called. None of these are talking about cycling through them. I don't think that it must track inside, but I don't see any register that we have to update to tell which one. So I think it just increments. I think I read somewhere else that it will just I think I read in this one, that it will just cycle through them. So let's start stubbing out our different driver, like our different calls. So we're probably gonna have a function write, and this will take in a packet, which will just be a U8 slice. Maybe. I guess a U8 slice here probably is actually incorrect. Because this write call, will it own the data? I was going to say that we have to wait for the driver to finish writing before we know that we can drop it. But if this is an async function, we can just make sure that it's done before we exit the async function. So that's probably okay. That's probably an okay API. And this is unimplemented. And we'll probably have a async function read. And this will return a packet. And will it be a slice? Probably I wonder if it being a slice is a problem. So in that circular buffer, after we read, we increment the data pointer. And the slice of data there is no longer valid after when the machine, like when the card might overwrite it. So maybe this should be a, actually a vec u8. Right? Because we'll probably copy it out and use it. But you could also do a, like, I don't like the idea of forcing a copy if we don't need to. You could actually take in a function that operates on that data. And the user of this call could choose to copy out if they wanted to. So I could say, like, on read, we call this f, where f is a function that takes in a u8. Right? That's not crazy. Maybe. Maybe it is. Yeah, who knows? And maybe this should also be an async function. Maybe. I guess we'll kind of try this for now and kind of see where this goes. This also, maybe this should be fn mute so that it can change data inside. There's a lot of like details here to think about, but we can always modify it later. I do like the idea though of not copying in the API itself. You could also return like a read guard that when you can hold on to this thing, and when it drops it, then the pointer is incremented. But I think that would hurt the network card performance, because we would be like, they could hold that, a user of this API might hold that forever, and then you could just never cycle through your ring buffer again. So that'd be a problem. So I think this is the best option for now. And we can think about it later if it doesn't work out. Okay, this is also unimplemented. And in our demo here, probably what we'll want to do is we'll have to do we'll probably want to write a packet, right? And then we'll probably want to read it back after. Test 2, 3, 4, right? Maybe we write a few packets. And then maybe we want to read some back. All of these will have to be await. Well, let's start with one single read-write loop for now. So we write a test, and we want to say packet. And we just want to say info sent test, all right, received packet. And core stir from UTF-8 unchecked. We'll just say, yeah, go for it. And then we await this as well. Okay. So we now have like our thing stubbed out, and we're crashing on not implemented right here. which means that we're ready to start like hooking up the APIs properly. So I think it makes sense for all of our initialization stuff that happens right now onto driver creation. I think all of that can stay. And it's really just this like transmission and receiving stuff that we have to move over. So for now, this actually just turns into transmit data and wait packet. And this just turns sorry, let me think. This was previously mutable, and I don't think there's any reason for it to be. So let's just delete this. Delete this. No, I think that's it. Yeah, there we go. So there's no reason for that to be mutable. This now needs to be self.base. And we need to call this unsafe. And on read, now we have to, hold on. Let's think about this. On read, we just call this previous log received data function, but instead of logging it, we just return it. So we have this here, and we can just return this slice directly. And this guy will return a U8. Okay. And then we have data is this. And then we probably have to call on read with the data. Easy. Okay, arguments of this function are incorrect, so we need, first this is self.base. This is unsafe. So the data comes out of the unsafe block. And on read will be called in the safe code. Like this, easy. And got a colon, or a curly brace. And what is deliking here? This takes in a mute, so I just have to say this is mute. But probably this also doesn't have to be a mute box U8, because we're not actually writing any data to this guy, I don't think. Let's see, as pointer. Yeah, so no writing's going on. Yeah, I think nothing's going crazy here. Cargo check. Yep, the linter doesn't like that I'm passing a box here. This can just be a slice itself. And this guy is already by reference, so cargo check. Anybody else mad at me? 236, he doesn't like this mutable that isn't necessary anymore. Okay. Chillin'. So cargo run. And sent test received something that's very close to test. So the problem here is that our log received data is not correctly, how do I say this? It's not, there's several parts here. There's header, length, and then packet. And we're parsing all of this when really we should only be returning the content of the packet. So we have the length parsed, we have the header parsed. Right? Let's write the header down as well. Like this. We wrote down the header. Read volatile. And oh, we actually already had this. Header is header read volatile, like this. Read volatile. We need to do volatile reads because we're working with memory, and Rust might assume that since it owns the pointer, that like if it writes and reads a pointer, that it might assume that that's the value of the pointer, right? If you do a write and a read, it's like, why would it be anything else? But in reality, hardware may access it, so we have to call it volatile. And now we should say that this should be header add 2 because it should be length add 1, and then the length should be returned. So let's take a look at that. No method named add for length. That makes sense. Let's just header add 2. Cargo run. And so now when we run this, we should see our own value came back. So we sent test, received test with some trailing shit. So let's see if we can figure that out. So length here. Give it a sec. So here we get length 64. Is this where I'm logging? This is in 192. Yeah. So header 1, length 64, capper this, CBR that. So the problem is that there's a minimum length of a packet, I think. And I think that might be a result of the Ethernet frame just being that large. Let's see. 7, 8 plus 12. Do I have to count this manually? Do I have to count this manually? Calculator. Okay, so this is 12, 16 plus 46 is wait, there's a minimum of 46 bytes. I'm assuming octet is byte. Octet. What is? I'm assuming that's a group of 8 people or things. So I'm assuming that those are bits. Let's double check this. So the 7-byte preamble SFD byte is this 7 octets, right? So 7, 8 plus 12 is 20. Plus 4 is 24. Plus 2. Oh, this is optional. So we're back down to 20. 22. 68 plus 4 is 72. So we're like, the minimum length of 42 is wrong. Oh, and that's because this is not part of the frame. Ha 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 ha. Okay, I could have just read 2 words farther, and I would have seen that they're claiming that the minimum length of a frame is 64 bytes. And so I think that the card is assuming that I will have at least 64 bytes, and so it's making that the minimum size. And so what I can do temporarily is just pad this right with zeros, just so that we are transmitting something valid. Obviously that this won't actually be correct if I actually try to send to somebody, but I'm trying to send to myself and just test that it works. So let's do that for now. And I guess we'll just assert that packet len is greater than 64. Oh, oopsies. Is there assert greater? Assert greater. Let's look at the assertions. Do I only have assert not equal and equal? Yeah, that's pretty reasonable. So we'll assert packet.length is greater than or equal to 64 just for now. And we'll kind of drop a fix me on here and say like runtime validation should return error. Crashing my kernel because we wrote an invalid packet. Wholly unreasonable. Okay. So now that assertion's failed, but now if I go back to main, I should be able to say test, this is a long test string that has to be at least 64 characters. There we go. So now we should see sent test received. This is a long test string that has to be at least 64 characters K. Still not quite right. So let's get rid of this from UTF-8 unchecked and try to do a checked version. So it's valid up to 64, and then there's a little bit extra. So it's possible that the length field that I'm getting here is a little too long. So we are saying received buffer length. We have that logged somewhere. Hold on. But I'm not getting to see it in the logger because I'm bailing out too early. Because I'm crashing because of this unwrap, so we'll just comment this out real quick. And received buff length is 68. Which makes sense because this length is including the header and the length fields, I guess. So what we have to do now is go back to our driver, and this should just be length -8. Wait, 8? No. -2. 68 should -4. Sorry, 68 should be 64. Oh, I don't actually know that. Why am I just assuming? I was assuming that this test string was 64 bytes long, but I don't actually know that. So let's just info or debug writing packet with length packet len. This is obviously what we want. What's it bitching about? Semicolon, not colon. So writing packet with length 64, that's actually really lucky. Okay, so it does make sense that this logging of received data, he needs to subtract the two 16 bits segments from the length that aren't part of the packet. So this is just length is -4. And now we should be able to go back to this here. And now we sent... This is a long string. It has, oh, oops, this is wrong. Const sent written string is a U8 slice. Is this? We use the written string here, and we now can say we can now pass this in here and print it out. Gosh, this is so... There's a lot to get right here. So we'll make this a stir that's static. And then we need as bytes when we feed it to the Ethernet driver. And we need to semicolon here. And he's saying we don't need the static here. There we go. Sent. This is a long test string that has to be at least 64 characters. Received. This is a long test string that has to be at least 64 characters. Boom. Okay. So we now have done a send receive to driver from main. And this was at approximately 50 minutes into stream. Okay. So what's the next thing we want to do here? We want to try two messages from driver to main. Because the problem here is that we know that we can send one, but we also know that the driver is going to behave differently on the second one. So we need to make sure that we're tracking all of that state correctly. So we'll do this again. And we'll say written string 2. And we'll just say this is another long test string. It has to be at least 64 characters. And this guy should be 2. And if we cargo run this, we actually just get our kernel hanging. And that's because we're, one, there's two things wrong here. One is we're not using async code to like validate this, and so we're never bumping out and waiting. But that wouldn't really fix it anyway, so we would wait anyways. And two, is we are not correctly transmitting in like the buffer. We're not like handling the buffer order correctly. So let's look at that. So this transmit data is just the way it works is we put the pointer to the data into this like data register. We then write the length of the data into the status register, and then we set this like go flag and we write it back. And then we wait for the transmission by basically like hot looping on this like status bit being this like bit that we set to say go. When it says it's done, it'll flip it back. And so all we have to do is make sure that we're cycling through all 4 of these like transmission descriptors. And in fact, we should probably check here that this isn't currently used. I bet you overwriting this while it's busy is like a big no-no. I would just bet. That seems unsafe. So first, let's, instead of taking in the base pointer here, we should take in the data pointer, transmit data pointer, which is a mute U32, and the transmit status pointer, which is a also U32. So now this guy's replaced with transmit status pointer or data pointer. And this goes away. And this is now transmit status pointer. And let's see, what else there is here? Transmit status registers. This is transmit status pointer again. And this is transmit status pointer. Okay. Now, when we call transmit data and wait, we say let data pointer equals the base pointer, so like where our mapped memory is at all. We add the data offset, but we don't just add that. We also have to add the transmit index times 4, where 4 is the size of the pointer. So we can say actually core mem size of U32 just for documentation purposes. This is like kind of clear to what's happening. And the status pointer is the same thing, but for status. Now we have to increment the transmit index equals, so that's this transmit index plus 1 mod 4, because there's 4 of them, which it says somewhere in the datasheet. I'm just going off memory, but if we look here, not here. Here we go. Somewhere. Are these not it? Here. Transmit status 0, 1, 2, 3, right? It's just there are 4 of them. Okay. So now this guy needs to take in the data and status pointers. So we just do this, data pointer, status pointer. And these guys have to be cast to U32 pointers for this to work. Now the only problem is that this transmit index doesn't exist. So we'll just set him to say transmit IDX is 0, or sorry, he's a U8 is all we need because we're only incrementing him to 4. And here we say transmit IDX starts at 0. I believe I read somewhere in the docs that that's what it starts at, but I'm not going to go back and find it. Well, we'll just see if this works. Oh, it doesn't like that these are... It doesn't like that I'm doing U8 plus U32 here, so we'll just say as usize here, and that should fix it. And here we now need to make this a mutable reference because he's incrementing this index. Okay. So cargo run. We now succeed in writing twice without like hanging, so that's great. But I think the second one, this is another long test string, and this is a long test string. So what we're receiving back isn't working because we're not incrementing the read buffer as well. So here, first of all, this is called log received data. Absolutely wrong word here. This is a get packet, right? And here, internally, we actually don't have to keep track of this like for state thing. We can just this is actually part of the driver or the card itself. It has a register in there that we need to keep updated, this capper register, or else it won't know what we've read, I think. Let's double check here again. Capper buffer read pointer. Yeah, so there's this buffer write pointer, buffer read pointer, and I assume when read hits to write, I think that it'll just stop, probably. We have to make sure that we're emptying it fast enough. So here, I think all we do is we use this guy as our base address. Let's see what he is here. We have it written down somewhere. So we see capper 0xFFF0. Now, what is the length of our buffer here? The length of our buffer, total buffer length is, we'll print this as hex as well, so it's easier to compare. And this is receive buff ling. This is the data that we've provided to the card, that like the region of memory that we've allowed to work with. And I just want to see, like, are we at the very end of that region of memory? So no. But interestingly, because the bright pointer starts at 0, with this actually isn't a problem. So I think that it probably sets it to something like this on start, just because it's like a big number that it knows is past CPR. And probably the default buffer length, if I remember correctly, there's like a bunch of different variations of this, and I've picked the max one. Maybe this is like the minimum size or something. I'm not sure. For now, though, let's initialize on start the read buffer to 0. So here, maybe we'll do it in this init receive configuration, where we say, no, we'll do it another one. We'll say init capper register, sure. So we have a similar function. This is init capper. This is capper offset instead of global receive. And we can just blindly write this to 0. And we can then say that the set val is capper read volatile, and we should know that the set val is 0. Cargo run, see if that crashes. Great, everything's great. And now we should be seeing capper is 0xFFF0. So what's odd there is I would have thought that when we initialize this to 0, the fact that we read it back here and we get 0, it's odd to me that later we don't get 0 without ever touching it. And why is that? It's because it is a U32 here, but a U16 over there. Let's try this. Attempt to subtract with overflow. That's interesting. Where could that possibly be? Let's just hello here and here and just see if we're getting all the way there. We sure are. Where would this be? Where would this be at all? Because all I'm changing is capper. So I don't understand why like any subtraction should change at all. We comment this out. It works again. We initialize this capper register to 0 and it breaks again. Let us double check that this is in fact a 16-bit register. It takes up 2 bytes, so it should be. So who is getting mad here? Let's comment out this read and see if that's related. Yeah, there's no anger there. Is it the get packet call? It sure is. Okay, that's giving us a good clue. So probably it's this, right? There is a subtraction here. So let's take this subtraction out and see what we get. Interesting. Oh, okay. So the problem is he's not right. There's nothing being written because I've initialized capper to be since read and write are the same, it's not incrementing the right buffer, the right pointer anymore. So it's not refusing to write data. So it actually does make sense to make, maybe we should initialize it to the opposite of this. Right? 1 less than 0. He doesn't like that either. I wonder why. Oh, because this is 16-bit. I wonder why he doesn't like this. Maybe because it has to be in increments of 64 or something. Or increments of 16. That could be why its default value is FFF0, is because it needs to be in some increment. That would make sense because it's only ever expecting to transmit 64-byte segments or something. Maybe. Whatever. We can actually check the QEMU source code for a clue. So let's look at their driver, and we'll look at their capper. Okay. This value is off by 16. Okay. Is that right? RX buff pointer. So where's this called? RX buff pointer, right? This is the register right, and this is RX buff pointer is 0x38, which is probably the same here as x38. Yep. So they are just saying that it has to be 16-bit. So that makes sense. Let's double check again. Right. Capper. So they're saying that we're writing this, and this value is off by 16. Let's see if we can find that anywhere. Capper, buffer read pointer. Sure. Val mod 2. What is mod 2? Define mod 2. Arg percent size where size is a power of 2. I see. So this is mod buffer size where buffer size is a power of 2. So maybe I don't understand. Receive. This actually isn't even what I'm trying to write, right? Buffer size, RX buff pointer. Let's see again. Yeah, okay. So there is a buffer pointer in here, and when we write him, he takes the value plus 0x10. And then writes, so that's, I don't understand why that would be, but sure. Maybe it's because it has to be one 16-bit chunk behind, because it needs to be behind. Yeah, because if it collides with the right pointer, then it's a problem. Sure. So, according to QEMU source, this has to be offset by 16 bits. Okay, yeah, sure. We'll live with that for now. So now on read, we have to update the capper. So if we first say that our start equals receive buff, right, as pointer plus capper plus 2. QEMU source says this is offset by 16 bits. And these actually shouldn't be plus, these should be wrapping adds, because these are this is a circular buffer, right? So wrapping add as usize. And now we have start and length. So we have start as u8, length as usize. And then afterwards, we need to increment this buffer pointer to be where we read to. So we're not ready to do that though until we've like handled the packet. So here we get it, someone like does something with that data, and then only after that do we increment the pointer. So we increment capper, we pass in self base, and we pass in data.len. That doesn't seem reasonable. We'll just say increment capper will take, it will like reparse the data and reparse the length and increment itself. And I think that's the only really sane way to do it. So, because then we don't have to like pass the data around. We don't have to like give back the slice and like reverse engineer the length. We can just ask the header itself. So, first of all, this is wrong. I've made a mistake here. The first thing we need to do in get packet is get our offset into the buffer. Then we can get the header. So this is headers like this, and length is header.add1, but this should be wrapping add 1. Right? Cool. Cool. We will have to test that when we get to the end of the buffer, we do in fact get something sane, and so we'll just probably later do a test where we do like 64 writes or whatever. So let's make the next checkpoint send, receive lots and lots of messages. Okay. So we've got this part, and this actually should probably be split into its own function, because we're going to do the same thing underneath here, where we say increment capper. So here we're going to do the same thing. We get the capper offset, and we get the length here, but this time we will not subtract 4. This should also take in receive buff probably as a U8 slice, because we need to read the length from the buffer. And then we just say capper plus equals length. And then he doesn't like that, so as U16. And this guy doesn't have to return anything, and we now just have to write that value back. And this again isn't a plus equal. This is capper equals capper.wrapping add length as U16. Now, this actually becomes a bit of a problem now that I'm looking at this, because here we're using wrapping adds everywhere, but here we actually are not. And because we're like assuming that the data is going to be like one contiguous slice, which is a problem. Header add 2. Sorry. So what we actually should do here is we need to update this API to return 2 slices, right? Because they may not be contiguous in memory. And then we can return. That way, if we wrap around, we can return the end chunk and the start chunk back to back. Okay. And then for the vast majority of cases, this will just be empty. And the second one will not be. But let's handle that later. So we'll say fix me, handle, wraparound on read. Okay. So here we never finished this part where we're incrementing capper, the pointer to this where we've read. And so we just say, hey, driver, or hey, device. Let's say that we have this register that we've pulled out. So you have let capper reg is this. We read from the capper reg. And then we write back to the capper reg. Capper reg write volatile capper. Easy. Easy, 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 easy. Let's also, this buffer is being used now, so let's just clean that up real quick. Receive buff. And we delete the underscore from here and here. And wrap this on unsafe. And delete this leading underscore. Start to run. Okay. So we are still in trouble. This guy is causing problems. So let's log him for now and just see what we get. So both times we read, we're getting 0 length buffers, which is a problem. And I don't understand why. I would have thought that it's related to like the initialization thing here. That's what we saw before. We had this like init capper, so let's try removing that. No, no good. Is it this increment capper? If I delete this thing that we just added, does it go back to working? No. What did I change so recently that this got fucked? It must have been this. Oh. No, this seems right. Header is this guy. And we should be seeing that header is 0, receive like, oh, 0. That's a problem. I see. Sorry. So, let start offset. This should be capper as usize wrapping add 2, right? And then this should be the receive buffer pointer, no wrapping add, start offset. Because what was happening was we were clamping our pointer to just always be between 0 and like U16 max, which is fucked. I think. Let's see. Receive header 0, receive buffer length 0, header 0, length 0, capper FFF 0, CBR, buffer length. Okay, so we still have problems. So this should be received header 0, receive buffer length 0. Absolutely, positively fucked. Let's print out here what we get for capper. So let's just say capper. And we get 0x FFF0, FFF0, which seems reasonable for the first time. Not the second time, by the way. That's a little odd. What about the start offset? Let's see what we get here. Start offset is start offset. Aha, 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 aha. I'm adding 2, but these are, this is now not in U16. This is in, bytes. So I actually have to add 16 here. So what do we get now? We get start offset 0x100000. That makes sense because this is a U32 probably. So we actually need to specify that this is U16 for this like wrapping add logic to work correctly. Now we still have an offset of 10000, which I'm surprised about because I think that this should be 1, 2, 3, 4, 2 bytes, 16 bits. So does this also need to be U16? Yeah. I see. So start offset. It's assuming that this has to be a U size because of where I'm using it later. So here I need to say, no, I'm certain I really want this to be a 16-bit number. And over here, we can now cast that 16-bit number to a U size. Like this. Oh, and I'm actually doing this like, this should be like this. It's because of this cast. So everyone here, these can be untyped. I don't need them to be typed. And probably now everybody is happy. Start offset 0. Perfect. Receive buffer length 64. Received header 1. And then here we get a 70-bit. Perfect. So this init capper can probably come back and which should still work. Nice. We still get 2 sane sizes. And now on read, we can call increment capper. And everybody's happy. And go back to main now, and we can go turn this logging back on. Oh, it is on. So why am I not printing what I got back? Let's double check this. So 1, we're not seeing capper incremented, which is a problem. Right, we're seeing here that it's 0x FFF0 in both of these. Also, received buff length 0 also seems wrong. So let's take a look skis at that again. CBR is incrementing as we would expect. Great. Oh, I was confused. I was seeing writing packet with length and thought that was reading packet with length. So here we've actually just got these length fields are totally fucked again. So let's take a look at those. That's on read. We have get packet. And his length is header, wrapping add 1, read volatile. This header needs to be as U16 because the header is 16 bits long and the length is also 16 bits long. Let's see if that changes the behavior at all. We're definitely getting closer. Definitely getting closer. Length, we already said, has to be subtracted by 4 here. And now we're definitely getting somewhere. We're back to saying this is a long test string that has to be at least 64 characters. This is a long test string that has to be 64 characters. So we've read it back here, and we're back to the state where we're not incrementing the capper correctly. Great. We're moving forward in the world. So let's see what we write here for capper. Let us see. So here we actually need to probably copy paste this shit again. Later we will factor this out, but for now I'm going to copy and paste it. So this is capper, reg, read volatile. We have start, we have header, we have length. We don't subtract the 4 this time. This is the part I've been like trying to get out of. And this has to be mutable. And this has to have to be like this. And now we are getting some problems still. So let's go back to main here and see these unwraps that are causing issues. So let's just pretend that it's valid all the time. And here we go. So we're really close. We're really close. We're saying this is another long test string that has to be at least 64 characters, and we're getting like fucked up shit. This is another long test string that has to be at least 64 characters. So it's just that our on the second read now, when we increment our pointer, we're in a slightly wrong spot, I think. So now what I don't understand is why that would be the case. Increment capper. Looking. So we get the length of our packet. We add it. We know that the length of the buffer after the first read should have incremented by 64 characters, the length of this string, right? We wrote a buffer of 64 bytes, and we know that we have 4 bytes of overhead, so it should be 68. So we also know that we need to be 16 bytes, or sorry, 2 bytes offset according to this QEMU source code. This value is off by 16 bits. Or off by 16. Yeah, 2 bytes offset. So this should be 64 after we write it, I think. Because... oh no, it should be 70. Here we've written up to 72. And we want to be 2 bytes back. That's what the CBR is like where we've written to. Let's think. Does that all make sense? Beep boop, doing the math. No. I bet there's 2 padding bits at the beginning and 2 padding bits at the end or something. Or bytes at the end. Let us read this guy. Let us see if he can tell us anything of use. So, transmission, I don't really care about, but what about receiving? We have a ring buffer, physical contiguous memory, data coming for the first time is stored in receive FIFO in the chip, blah, blah, blah. Then move to the receive buffer when the receive threshold is met. Yep. CBA keeps the current data as the data moves to the buffer. Capper is the read pointer, which keeps the address of data that the driver has read. Right. Keeps the address of data that the driver has read. Okay. The status of receiving a packet is stored in front of the packet header. So, why is me incrementing it by the length? I guess I haven't actually like properly verified that that length field is right. I've just kind of assumed that that's there based off of like experimentation, but I actually don't see anything. Aha. After the whole packet is read from the FIFO, the receive packet header, receive status, and packet length is written in front of the packet. CBA is updated to move to the end of the packet. Okay. So, software issue. We need to update first dismiss the interrupt. So first we need to write capper and then write a 1 to RX is to the interrupts handler. Okay, sure. Which I think we're probably just blindly doing no matter what. But he doesn't say what to write to capper. When wrap is enabled, we'll move the rest of the packet data immediately after the buffer. This will make the last packet of the buffer continuous. But the receive buffer has to have 1.5k more space at the end. Okay. Okay. So, where is he updating capper? Capper. So here you have some sample code. Income packet is the read pointer plus 4. That's close to what I saw before. Is that like I'm skipping the first 4 bytes, the header and the packet length. They actually have the structure like this, so that they don't have to do offsets like I'm doing. And where do they tell us about the read pointer? Okay, read pointer offset equals the existing pointer offset plus the packet length plus 4 plus 3 and okay, well, 3 for D word alignment, 4 for packet length, 4 for the header length. Packet length includes 4 bytes CRC. Oh, okay, so the length is 4 extra, not because of the header, but because there's just a CRC at the end, which actually means that we should actually look at the CRC. Okay, sure, but that makes sense. So, length, we can just actually come back here and we say, when we get the length, minus 4, packet includes a 4-byte CRC at the end, which we don't want to copy. And here we just don't do that minus 4, but we have to add 4 for the header. Add 4 for the header and packet length. So now, when we run this, we have our first write. This is a long test string. We get this is a long test string, blah, blah, blah. And then here we have our second write. This is another long test string. And received, this is another long test string, blah, blah, blah. Solid. Very, 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 very cool. I'm pretty happy with that. And now we can probably go back into from this like unchecked UTF-8 parsing, and we can probably just say from UTF-8, target run. And I have to unwrap this. Oh, fuck. Yes. Okay. So we can now send and receive 2 packets, which is a lot better than before. We could only send and receive 1. So this is done now, and we can say that this happened at around 010800 into stream. Okay, so now we want to handle this like wraparound bullshit. And I was just reading that I set this wrap bit, wrap, baby. When set to 1, data will keep moving the rest of the packet into the memory immediately after the end of the RX buffer, which just means that we need at least 1.5k extra bytes than we tell it that we have. So we've like told our configuration. We've told it that we have 64k, right? 64k plus 16 bytes. But now we just have to add like another 1.5k on top of that. So somewhere in our receive buffer, configuration register BSB1 says that this is the size. We also need 1.5k extra space due to wrap bit being set. Easy. And so now we just say 15 times, or 1.5 times 1024. So this is actually, since we're doing integer math, this is 1024 plus 1024 over 2, which is 512. So 1536. Okay, very nice. And maybe this calculation is getting a little bit too much to just shove in there. So we can say const 64k or do I have to really write like size? I don't want to like, you can't start a number with a variable with a number. So we say const buff size is a 64 times 1024. So we'll say like const data size, I guess. Const overhead equals 16, and we'll say const wrap padding equals 556, and then here we'll say const buffer size is the data size plus overhead plus wrap padding. And then here we just say buffer size, easy. Okay. So now what we want to do is we want to write like so much data that we overflow all the way around, which means that we have to do over 64K of writes. So we know that we have 64 bytes here. And so let's then just say for I in 0 to 60 to 1024, right? Because that's 1K. We'll write 64. And so we should definitely wrap all the way around by doing this. And instead of logging, we'll assert that the written string as bytes is what we get back in the packet. And here we'll do this again, but with written string too. And we'll say packet, we'll write a format string here, maybe. Let's just see if this fails first, and we'll come back to it later. Attempt to subtract with overflow. Okay, so there's definitely a bug here still. Let's try doing this with 10, right? Let's just see if 10 of these works. No, 10 doesn't work. 2? 2 also doesn't work. So really, we only can do 2 writes. We can't even do 4, which is kind of interesting. So let's take a look at what happens on the fucked up one. So we have another attempt to subtract with overflow, which I almost certainly know is coming from this like length -4 shit, right down here. And we can just confirm this by not subtract the 4. Oops. Let's take out these assertions temporarily in main that we know are going to break when I do that. And we got a little farther. So here, this length -4 caused a problem for sure, right? But then taking it away also caused problems. So let's take a look and see what these like start offset is on when it fails. So here, print that out. And where do we have it? Start. Oh, we probably should write down start offset is this. So start offset 96, attempt to subtract the overflow, and let's print line the length here, or the header. And let's print line the length before we subtract 4. So let's do this in 2 steps. We'll say let length equals length -4 here, and we'll print the length here. And this should say length is length and header is header. And this should be read volatile. Okay, so we get a start offset of 0x96, no header, header of 0, length of 1. So something's not right, clearly. Let's think about this a little bit. So is 96 hex an appropriate offset for us to be at here after writing 2 things? Let's not print this in hex so that I can do some math on it in my head. So the first offset, 0. Great. Second offset, 72. Also makes a ton of sense because the second offset is 64 plus the 8 bytes of padding to get us to 72. And then we have a 68-byte string, I think, written after. So we should have 72 plus 68 plus 8. 148, but we are at 150. Let me double check that that 168 is correct. So here we should say print line written string 2.len. So this is length 2 is like this. Quit real quick, cargo run. The second length, hello, written string 2, print length. Oh, here, 68. Length 2, 70. Oh, so it is, this is right then. If like the length of this second string is 70, then we should have had 72 plus 70 plus 8. So 72 plus 70 plus 8 is 150, and that is the offset that we're getting here. So then the question is how come on the third write, how come our received data on our loopback is just like fucked, right? Like here, this was good. Here, this is good, and here it's just like broken. What's different this time? What is different this time? I wonder if we're like, let's look at the right side of this, I guess. Like if the read side, we know that our pointers are sitting at what we think are reasonable spots. Why would we be struggling unless the right is failing? Right? Let's see if we can like try to convince ourselves that that's the problem. So transmit data and wait. He uses the transmit index here. And let's just, as for debugging purposes, let's see what pointers we're using here. So let's say let data offset, and we'll take this shit shown here, and we'll do it like this, and we'll actually log the data offset. So print line data offset. And what we expect to see here is if we are handling this correctly, we should see this match up with the data offsets in the datasheet. Right, so we should see, oops, I have to write, I keep forgetting that in my prints I have to write down what I'm doing. So we'll say the data offset is this, right? And here we say 20, 24, 28. Another thought that I'm having is, what if the interrupts are causing problems here? So we have confirmed that these 20, 24, 28, those match these guys, 20, 24, 28, right? So there's nothing wrong with our like tracking here of index. But it could be that the first two sends happen very quickly with each other, right? And the ones afterwards take a little longer. And it's possible that because we're not handling our interrupts correctly, that we are not allowing the card to transmit the way it wants to. So let's see if that's a possibility. Here we do in fact clear the interrupts as we are supposed to, so I don't think that that would be the problem. The fact that transmission are... Okay, sorry. Rapidly thinking. Let's add an extra offset variable here that's this calculation that takes in like the additional number of bytes that we have to offset. So we have data offset is transmission data offset plus extra offset, and the status pointer is let status offset is this guy plus extra offset, and this will be status offset. We print out the data offset, we print out the status offset, and we have to log that as well. And so do these guys also match up? Status offsets should just be the same, but plus 1 in hex. So we have status offset 101418. And here we have 101418. So nothing wrong there either. So transmission likely is working okay, right? We've taken the status pointer, we use that as our way to wait. He's getting his bytes triggered correctly, and so we shouldn't be trying to read until the data's written. So why would on read we get the first two work and the second one doesn't? Thinking. If our receive buffer was not actually the right size and we're corrupting memory, that's an option. So let's look at the receive buffer generation and just kind of like sanity check that logic. So we generate a receive buffer, and let's just times 10, right? Just for sanity check. And we do, in fact, see the same behavior where our offset is right, our header is not ready, and our length is not ready. I guess we are kind of assuming incorrectly. Sorry, let's just undo that times 10. That we're incorrectly assuming that the read is immediately ready after the write. That's just like almost certainly untrue, right? And so we actually have these print lines of status register value. But all 3 times they do indicate that read is okay. Let's make sure that when we write, we should probably be writing a 0 back here to clear. Oh, that's not good. What the fuck did I just do? That was fucked up. Read and write the register. Okay, let's look at this like clearing register shit. Okay, so here in the interrupt service handler, they are saying that they read back after they write out that it's okay. Seems pretty reasonable. Seems pretty reasonable. Transmit, okay. After the on bit has been set by hardware, indicating DMA transfer is completed, the hardware will start to transmit the packet across the actual network. This bit will be set to 1 after the network transition has completed. Okay, so maybe we are polling bit 13 for when it's ready, but maybe we should be polling bit 15 for when it's true. Right? Cargo, run. No. Okay. So somewhere, I mean, I know for sure that we're not handling this correctly, right? Like, we know that we're just kind of writing and assuming we'll get the read back immediately. And we are not seeing a read okay at the start of our packet. So I wonder what happens if we poll on the read side for the header to have an okay. So we can say loop, right? And we can say while if header read volatile get bit is not equal to 0, break. Right? Because we could say that, like, maybe the header of this chunk of, like, it's not been written yet. Cargo run. Let's see. Yeah, so he doesn't like that. Let's take this printout and see. So the first one succeeds, great. Second transmission succeeds, great. Third receiving never ever ever gets a 1 in that. And you really got to ask yourself, why the fuck would that be the case? Do you think it's something to do with this loop? Do you think that if I write a third packet here that's different than the other two, it will behave any different? Like, almost certainly not. Right? Almost certainly not. But let's see. That's comforting in some way, that we know that that's in the same state. Very interesting. Very interesting. What else could we do to debug this? Maybe in here, is there a possibility, that the third one is not being handled correctly? So, TX status. Right. What do they do in the QEMU driver here? They attempt to start the transmission and mark the transfer as completed if this doesn't fail. But what if it does fail? Let's try. Maybe there's like a queuing problem here, and let's actually just chuck a sleep in here, right? Let's just see what happens. Maybe the QEMU VM needs some time to think. No, right? That sleep doesn't help us. We are not advancing still. This is very odd. Very odd. Do you think the data's in there at all? What if, here, we just say, length equals, if length is greater than 0 for, we do this. Else, we say length equals 64, because we know that this is only they were only getting problems in this like third failing case, so we know that this is only going to be taken in the third failing case, and we can actually then maybe extract some information about what's in the buffer. Is there a loop here still? Yeah, let's get this fucking loop out of here. So let's see. Let's log out what we get back here. So we'll say print line packet 3 is some debug representation of packet. So there's like shit in there, which is kind of interesting, right? And we'll say or stir from UTF-8 unchecked, because I don't care if there's invalid data in there. Let's just kind of see what happens. This is a third long test string. Okay. Okay, so that's interesting. So we are in fact getting data in there. And it is fucked up. But it's not immediately, which it should be, right? Because if we log the other strings, these guys line up perfectly, right? If I get this right, cargo run. So it's actually like 150 is wrong, right? This start offset 150 looks like it should be like 154 maybe. So it's something to do with our like read buffer incrementing that's not working correctly. So let's go back to this data sheet and see if his increment works. And Rx read pointer mask. D word alignment. Fuck, I forgot that part. Okay, let's try doing that. Okay, so what that claim is that this increment capper doesn't need to be just +4. It needs to be D word aligned as well. So, +3. And we need to mask this with the inversion of this, I think, because D words are every 2 words. So 1 word is 2 bytes, I think, and double words is 32 bits or something. So D word alignments is every 4. Then D word align with +3 and mask. I think that's right. Let's see. Okay. 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 Very nice. We're getting somewhere. Okay. So we missed the constraint here because it was not really like, well, maybe it was listed because I can't read. Maybe. Or maybe because it's not listed. Who knows? One of the two. But we just didn't use this D word alignment thing. So that's why after the first string it works, because we just happened to have a D word aligned string length. But then since it was the next one wasn't, then we had problems. So let's go back to looping here and see if we can say for I in 1 to 10. Let's see if we still get the right thing. So where this is a third, this is another, this is okay. So those they're not like horribly corrupted. And now what we can actually do is we can add these assertions. So we can assert that written string is written is what we get back. Right? So we just say as bytes. And we'll do this again down here for a written string 2. And we'll do this again for written string 3. And we'll cargo run. And if we don't crash, we're chilling. And we didn't crash. Let's go, baby. Okay, and so now we've done this, let's just crank this out 10, 24 times to see if there's like any issues with buffer wrapping. Oh, too many logs now. Okay, so let's, our log buffer. Okay, so what happens is we shove some things into our log buffer, and then we service him every once in a while, and we say like, please like clear up some of the shit in here. And if we write too much before it ever clears it, then we crash because that's just what I do every time anything happens. But really, let's just turn that crash off for now and just see if we do not crash for another reason. Oh, mwah, 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 mwah. Okay, so it looks like we're chilling. We've sent and received lots and lots and lots of messages. So this is at around 1 hour and 34 minutes and 15 seconds. Very, very, very nice. Okay. The next thing that we probably want to do is actually make this async. Because that's actually part of the reason that the log buffer was filling up, is because this guy only gets serviced when somebody else is like waiting on something. When like the async thing kicks in. So let's start looking at like what does that look like. But let's first commit sending and receiving lots and lots of packets seems okay. Very nice. All right. Okay. So, yeah, I guess it's this transmit data and wait. He's doing this like poll here. And what he should instead do is he should wait for the interrupt to fire. And when the interrupt fires, then it's okay for him to continue, right? So we actually do register an interrupt handler. And here we can just say wake up executor, right? And that's maybe we should store, like stash what the last status register we got was. Or clear it in some way. It's kind of weird that we write back what we got, but then when the next interrupt fires, we don't know. Maybe when we write when we start a write, the interrupt status register gets updated or something. I don't know. We'll just kind of like we'll just wing it for now and see what happens. This is almost certainly going to have a bug in it. So what happens? Here we have a future, right? And we say when we write, we want to wait until it's finished. And so this loop that we had before here, actually, where'd it go? I thought I deleted it. Oh, no, it's here. This loop, we just need to do the same thing, but instead of pulling the own bit on the transmit status register, what we'll do is we'll just wait until we see we will check it once, I guess. Let's double check what this diagram says we should do. Use 4 descriptors. The 4 descriptors are used in round robin, right? So we go over each descriptor, and how we know when the transmission of a given descriptor is done is when the own bit is set back down. So probably what we should do is we store the address of the pointer that we're looking at, right? Instead of just spinning here and looping on it, we just say struct transmission waiter, right? And he has one thing in here, and it's the transmit status register, right? And what he does is he implements a future so we implement future for transmission waiter, which has to have a poll function on it. The output will be nothing. We don't really care. We just want to like look at him. And what he has to do is he has to check this, right? So he just says, we read our register, transmit status register, we read it, and oops, what doesn't he like here? Transmit status register, probably unsafe maybe. And if the own bit is set, if own, we return poll ready. And else, we return poll not ready, pending, right? So now what will happen is we will wait for this, we'll call this, and if it doesn't work, then we will go do something else. And when this interrupt handler runs, because like this finished, this will get pulled again. Easy. So here we need a future wake up executor, which is kind of like not how we should be doing this, but that's okay for now. Really, this guy, we should probably pass in this like handle to wake up. We should like register a new interrupt handler and check it, like use that to wake ourselves up. But we know that we're going to be using our own executor, so we can just like wake it up directly. Fuck it, whatever. I don't want to like deal with that piping right now. Okay, so now here, instead of wait for transmit, this is now like an async function. Async unsafe function. And here, instead of wait for transmit, he constructs this feature. So let f equals transmission waiter new. I guess we just do this. We'll just pass the register in directly. Transmit status reg. I'm renaming him so that his name, I can just pass it in by name here. Right? And I can just call f dot wait. And we'll just rename this as well. Transmit status reg. He doesn't like that. Transmit status reg. What does he like? A local variable with a similar name exists. Transmit status reg. How is this not the same? Hello? Transmit status reg. Oh, status. I see. Transmit status reg instead of status reg. So now in theory, we should wait still, and we should do the same thing on get. Where we say we do the same thing but with the header, but we'll think about that after. So let's fix this like length bullshit that we've had hard code in there. And probably this transmit data and wait needs to be awaited. Now our assertions are failing, which is interesting. I wouldn't have thought that this changed anything. Let's look. Oh, is my wake up executor in the wrong spot? This goes here. Probably shouldn't matter. Still broken, I bet. Yep. And this is actually looks like it's on the, maybe the very, very first read is where it's failing. And so it's just that it's going way too far, right? Like, here we have just extra shit on the end. So why would that be? Let's just double check if it's like a mistake here, where if I just say wait for transmit. Do we go back to the old behavior where it works? No, so it was already broken before that. Hey, what's up? So why am I just trailing extra data off the end? How many bytes is this? 1, 2, 3, 4. I'm trailing 4 extra bytes off the end. And it's probably because of this like increment capper shit that I added before. Let's just, no, this is the first one. The first one's fucked. So on first write, I'm also a Rust guy, but I don't have my own OS. Well, one day if you're really bored, maybe, you know, it's just one of those things. Okay, so I'm trying to figure out this data that I sent is very close to the data that I received, except the data I received is 4 bytes too long. So it's probably just in my receive. I probably just fucked something up when I was refactoring. So in get packet, length is this. And this is supposed to be at -4. Okay, so the length of the packet I receive has 4 trailing bytes for the CRC. And before I was removing that, and when I refactored, I accidentally just like pulled that out. Refactored, removed that if statement. So now if I run cargo run, I have dropped logs again, right? But I think that we are running to completion now. which is a good sign. So let's just reduce the amount of packets we're writing real quick, just for temporary check. And yeah, everyone's chilling. Sick. I'm running a protocol layer for Minecraft protocol currently though, so not totally unrelated. Nice. That's fun. Yeah, I guess it's close, right? I'm going to be writing protocol layer stuff soon, but before I get to anything like implementing TCP or UDP, I just have to like be able to like fucking like put bytes on the network, and that's where we're sitting right now, or we're not quite there yet. Okay, so I've got this like write async code is now working correctly, and what's kind of cool is now we're starting to see like logs interspersed with our print lines that are like completely synchronous. So we're actually seeing ourselves like actually have to wait and do something else temporarily, which is kind of cool. Oh wait, is that true in any way, shape, or form? Yeah, that is. Okay, so now we have to do the same thing with read. And I guess what is the check for if a read is ready? It's probably something like if the circular buffer that the machine is like that the network card is writing to, if it is incrementing the right end of it after everything's already in, which it should, then I can just check if the read and write are far apart from each other or not. So the process of packet receive, data received from line. Sure. After the whole packet is moved from FIFO into receive buffer, the receive packet header is written to the front of the packet. CBA is updated to the end of the packet. So yeah, we can just check if CBA and capper are close to each other, where those are like the two ends of the circular buffer. Does your Ethernet driver use async read and async write and stuff, or just plain old arrays and buffers? Okay, so the concept of like async read, I think, is like a very high level abstraction, right? This is, well, very high level by some mechanism. This is like something that isn't part of like Rust core. This is something that like Tokyo, I think, has implemented on top, if I understand correctly. I think maybe Futures Crate has it. Futures. I can't remember if these are like mirrored by Tokyo or if they are Tokyo only. Yeah, Tokyo Futures are. So I am using async code here. In fact, that's what I'm implementing right now. Except that I don't have something like Tokyo, because Tokyo is a wrapper around Linux calls. So what'll actually happen is Tokyo will have is like going to use, I think they call it MIO under the hood, which calls into like Linux epoll to say like I'm gonna wait on like 40 sockets, and when one of them's ready, I'm gonna like do something with it, right? I don't have Linux sockets. I don't have sockets at all. I don't have stack shit. And so what I have is I've basically like written my own really basic version of Tokyo. So it's like very, very, very basic, right? All it does is it calls like future. It like takes in a future. It polls shit. It just like polls all the future, which turns into polling all of the features that are inside it. And if there's nothing to do, I halt the CPU, because like I'm the kernel, I can do that if I want. And then in interrupt handlers, when something interesting happens, I just set this like atomic boolean to true, and then the CPU automatically wakes up and it knows it's time to poll again. So that's all. That's really all it is. And so now all I'm doing is I'm like implementing a future that will kind of map these like on interrupt, give me what I want. And so that's why this like, where was I a second ago? Like this is what my async write looks like, is just like look at the data on the network card and see if it's done writing. And if it is, then I'm good. And if I'm not, then I'm not. And the interrupt handler will wake me up when I need to be pulled again. Pretty fun stuff. So now I have to give that same. Always want to do something close to the hardware, like implementing some hardware driver. Yeah, it turns out that it's not actually. I would argue, with a very large bias from a firmware background, I think that like using a closed source library for C++ is like miles harder than writing a firmware driver, or like writing firmware for something, or writing a hardware driver. Because usually what you get is you get this PDF and it tells you how to interact with it. You get this other PDF, and it tells you like what all of the lines on the chip do, and like what all of the registers inside do. And it's just like the same thing as working with like an external library with documentation and API, except they can't change it. It's like it's the same forever because they're manufacturing millions of these chips. And they're not going to like redo the die. Like they're just going to keep going. They're going to document the bug and just keep going. Where on like software, you have to work on this like moving target. It changes and changes, and you always it's harder to get inside. It's harder to see what's happening. It's just I like this better. As long as everything is well documented, you don't have to guess from preparation stuff. Yeah, but I think that you have the same problem with normal libraries. With open source software, it's easier, but yeah, I agree. Anyways, it's not like a mystical field or anything, and if you want to get into it, it's fun and accessible. So I would go for it. Okay, let's make a async feature that checks for if we are ready to read. So wait read. Or maybe I won't make a feature. Maybe on read, I'll just return immediately if it and with nothing ready to read if it's not ready. Is that a better API? Say I have a, how am I going to use this? I'm going to have like some sort of like big main loop, and in him, he's probably just going to wait for data, and he's not going to poll. He's just going to say like, yo, when I get data on the internet, like from the internet, I'm going to do some shit with it. So I guess in that case, if that is how I want to look at this, then it makes a lot of sense for me to have an async thing that just sits there and waits for a packet and does like just blocks forever. I think I'm okay with that. So I'm going to do that. So I'm going to have this transmission. This is going to be like a read or receiver waiter. And he's going to have the capper register. He's going to have the CBR register. And I think both these are U16s, not U32s. And he is ready if capper, if self.capper reg read volatile, so we get the data from the hardware. If this is not equal, sorry. So from earlier today, we found out that the ring buffer head capper is going to be 16 bits behind the right where we should actually read from. So we say if this is plus 16, not just plus, wrapping add because it's a circular buffer, wrapping add 16. If this is equal to the CBR register, that means that there's no data. So we can say this is pending. Else we are ready. Okay. And now getPacket is an async function. He has capper. He has CBR over here. Why are those brackets around read volatile needed? Because I'm this is actually like a two-stage thing. I'm doing like let val is this. Oh, you're right. The brackets aren't needed. I thought that I often have something like more complex in here, so I just thought there was, but you're right. You're right, they're not. Good catch. Where was I? Receiver, waiter, get packet. So we have the CBR reg is, we'll say, let capper reg is this shit. Aha! This is an example of why I have brackets around read volatile, is because I need to cast before doing the read. Because if I read this as like a mute U8 instead of a mute U16, then I won't read the right amount of data from the card. And actually, like the card, as far as I can tell, like rejects reads and writes in some cases. They'll just like return you like the wrong data, or it won't write the data if you're not using the right like instruction. Like if I'm like move this register that only holds 8 bits into memory, that'll turn into like lines on the card, and the card will go like, I don't know, you didn't fucking write anything, like go away. That's my like. I think that's might be wrong, but that's at least how it seems to work from like a software perspective. So that's how I'm modeling it in my head. Okay, so I have this head and tail of my circular buffer in the card. Now I just say I receiver waiter, which is my future, that will wait for these two things to line up. I can pass in kappa reg and CBR reg, and I can just await that future. And now, at this point, it should be good to go. So, I before E except after C, so here I must have misspelled receiver. This is EI. EI. And probably now everything just works. I just have to make sure to like in get packet, I need to await this now. And cargo run. It doesn't hang forever. It makes it to the end. We're chilling. Big chilling. I like that. Okay. So I think that we probably accomplished send and receive buffering at some point during this. We did also end up hooking up interrupts to the send receive loop. We have not done like any of the like PCI registration collision or register management, but I think we have like accomplished a fair amount tonight. How am I testing my driver? Oh yeah, that's a really good question. That wasn't clear. I covered that at some point, but it was before you popped in. So this RTL 8139 has this like loopback mode, which is like he says normally used to verify logic operations up to the Ethernet cable. In loopback mode, the transmitted descriptor just like gets shoved right back into the read buffer. So this is like useful for them for testing hardware because they can test that like if they go all the way out and then all the way back in, it comes all if you get the same data, then like your both sides are working correctly. But I can use that to say that like every time I transmit data, I should just get the same data back. If I enable it. So I've got this like enable loopback thing here where I like set that field that they're talking about. And so then in main right now, all I'm doing is I'm just saying like when I write something, I should just get the fucking same thing back. Okay, let's just check again with like lots of data. Very nice, except that again we get to the point where we're writing so many logs that we like can't possibly service them in time, which kind of sucks. So I'm gonna have to think about that a little more later. But the core of this is working. Like if I comment out the logger issue, this does in fact make it all the way, and I do not like assert or anything. So I'm pretty happy with that. So we kind of got to the point where we can send and receive something. We can send and receive multiple things, receive lots of things. And we've got like our async code set up so that the interrupts are correctly waking us up when we need to be woken up. We've got like send receive buffering. I think what I was talking about here is like when I receive, if there's nothing to wait for, we should wait for something. And so like let's actually check here. We can confirm that that's working. Where here, if I try to read something, what should happen is this should just like block forever. So let's just double check that. Yeah, it does in fact look like we do block forever, and I'm sure that if I hook this up correctly, and ooh, we could actually probably test that. I wanted to test that now. So we could actually, let's do this. Let's comment out all of this debug code. And let's see if I write like a little future that says, let's send is a async and using a QEMU VM. Yeah, that makes sense. Like, am I actually using the hardware? No, it's just a QEMU driver for now. Although I'm sure that if at some point it would be fun to get like the hardware together to test it on real, but that's far down the line if we ever get there. So what I can do here is in my send feature, I can actually do a sleep because I have an async sleep set up. Actually, I'll just copy paste this. And let's sleep for a second before we issue a write. And we'll just do like, let's use words guessed. A long test string that is over 64 bytes long, or else it will crash. Right, we await this. Then we can have a receive is an async function that just does a RTL 8139 read that takes in a packet and prints it. Packet. And we can say like core stir from UTF-8 unchecked. Just so we can like see it logged nicely. And then we can do futures, future join, send, receive, dot await. And what we should hopefully see here, if everything works right, is we should see that we wait a second before printing and before sending and printing what we received. Oh, fuck. Right, because write is a mutable thing here. So let's just make this immutable, and we'll change this transmit IDX to an atomic U8 for now. Sorry, not immutable. No, that's right. Take by immutable references are immutable. And then we need to use, what is it? Core. It's in Rust core. Core sync atomic U8, and we probably also need the ordering shit. And I like this down here. But, you know, really, like, using atomics here is, like, maybe incorrect, because in reality, should we be able to write to this without, like, if multiple threads tried to write this at the same time, would we start to see problems? I think we actually would. We'd, like, clobber each other. But, no, yeah, that's fucked. So I actually can't do that. So instead, what I can do is we'll use my only synchronization primitive and try to make this usable for multiple contexts at once. So we'll put this in a RC interrupt guarded, which I just am using to say that things can be used for multiple contexts, and interrupt is the only thing that can block us. And that's not going to work either. Fuck. Maybe we just lie to the compiler. Yeah, let's do that temporarily. I like that. So I think that you can do like a reference counted and unsafe cell of this guy. And that will let me just like bypass the borrow checker and use them directly and just say like, screw you, I know what I'm doing. Just for this test. For later, we'll fix it. So this needs RC, new, ref cell, not ref cell, unsafe cell, new. This. I don't have unsafe cell imported, so let's just quickly pull that guy in. So this is cell, unsafe cell, like this. Best idea ever. yeah, just tell him to shut up. So here we can say let. Oh, I probably didn't need the RC actually. We'll see. So we'll call this get. And then we will dereference him, so like this. And here we will also get and dereference and read. Let me do it. Let's just undo these atomic things that we tried to do here. So that's a normal U8 now. And we tried to log the MAC at some point, and let's just fix that as well. Log MAC. So we'll just disable that for now. So here I didn't see. So I sometimes wish the dereference alpha was available as some kind of postfix. Yeah, dude, the arrow in C++ and C is like so much nicer. I need to await this. So here I should see. Oh, hold on. There is some extra logging on here. So let's go bigger than 1 second. Let's say that if we'll wait 3 seconds, and if we see us pause for 3 seconds, 3, and then print the right stuff, mwah, oh, that's sick. Okay, so we've actually just like proven to ourselves that both the sending, like the receive buffering is working, and that it will like correctly print the right string, and only when it gets something in from the network. So that's pretty slick. So I'm happy with that. I think that's like a good place to call it for the day. We've kind of got the driver hooked up. We've done all the interesting stuff of setting up async and getting like network. We've proven like the transmission and receiving that doesn't like have problems around the circular buffer. And now all the thing, like everything that's left is just like cleanup. So I'll think about whether or not I want to do that on or off stream. But next up will be either driver cleanup or some form of like starting to build up like Ethernet frames and UDP and TCP and stuff like that. So if you enjoyed what you watched, I'm on most days on Twitch at around like 2 Pacific time-ish. And if you want to catch up because you missed something, you can always check me on YouTube in the link description. Thanks for watching. Catch you on the next one. Bye.